everyone. So I'm going to discuss a sample problem about the thermodynamics and heat transfer. This problem can be found in chapter 5, the second law of thermodynamics and its entropy. So in this, we have this problem. A reversible adiabatic compression technique raises the pressure of helium gas from 60 kilopascal and 30 degrees Celsius to 350 kilopascal. So determine the final temperature and the work done assuming the process takes place in a piston cylinder device and in a steady flow compressor. So here is the given pressure. We have the pressure sub 1 and pressure sub 2. So pressure sub 1 is 60 kilopascal and pressure sub 2 is equal to 350 kilopascal. In this temperature, the Celsius is converted to Kelvin, so it is equal now to 303 Kelvin. So 30 plus 273. So these are the following specific heats and specific heat ratio of helium. So it can be found in the property table, in the table A2. From this ideal gas isentropic relation, so here is the equation for this one. We have the temperature sub 2 is equal to temperature sub 1 multiplied to the pressure sub 2 over pressure sub 1. So it is raised to its specific heat minus 1 over to its specific heat ratio. So it's specific heat ratio. So substituting those given numbers, and we'll get this, calculate this, and we'll get this 613.6 Kelvin. So we take the air in the cylinder as the system. So the energy balance for this stationary closed system can be expressed this as a net energy transfer by heat, work, and mass equal to the change in interval kinetic potential energy. So here is the equation for that. This is, so the work in is equal to the specific heat times to the change in temperature. So by using this, let's substitute the given numbers to this equation and calculate this number, and we'll get this final answer for 967.7 kilojoule per kilogram. So this is in piston cylinder device. So in letter B, if the process takes place in a steady flow device, the final temperature will remain the same, but the work done should be determined from an energy balance on the steady flow device. So here is the rate of energy in is equal to the rate of energy out. And this, the rate of the work in plus to the mass of the flow rate times to the enthalpy. So we're here, and this is equal to the change in enthalpy, and this is equivalent to this equation. The work rate in is equal to the mass times to the specific heat times to the change in the temperature, and let's substitute that to the given, and we'll get this final answer 1612.8 kilojoule per kilogram. So that is for the steady flow compressor.